Welcome to the Gemini Show. I'm your host, John Castor.
And my name is Annie Collins. Hey, John, who do we have today?
So, today, he's the youngest ever to get a PhD in astronomy. He's the youngest ever to be scouted by NASA. He's the only student to have ever graduated in 3.14 years. He is Dr. Peter Pan from Neverland University.
Hi everybody.
So, if you don't mind, can you explain to us what you do?
Well, I got a PhD in astronomy, and as you generally know, that is the study of space and every aspect of it. I study stars, galaxies, planets, and also the physics and chemistry behind all of this. That's what we study.
Sounds like fun.
So, what do you do exactly?
I calculate the distances of stars from Earth.
And how do you do that?
I use a specific branch of math called trigonometry. I also use parallax.
Then how do you apply it?
Well, let me give you an example. Say you are standing on the certain side of the Earth, and you, the Earth's core, and the Sun create a right triangle where the Earth's core is the tip of the right triangle. Using data such as the distance from the Earth's core to its surface and the distance from Earth to the Sun, and the angle at which the line between you and the Sun inclines, you can use trig, in this case, you can use the sine of the angle to solve for the hypotenuse and get your distance. You can apply this method to finding the distance of any star from Earth.
It's that easy?
Yeah, however, scientists have special units of measurements for this. Let me show you how it's done.
Alright, we'll be right back with Dr. Peter Pan's explanation in a short while. We'll see you later.
Finally on break. Hey, Dr. Pan, you guys want to hear some jokes?
No, not this again.
Well, someone's listening out. Alright, ready? What do you do when you're bored?
I don't know.
You change your calculator to rad. Isn't that funny? Okay, fine. One more. What did the complementary angle say to the isosceles triangle? Nice legs. You get it? Because it's a complementary angle, it's complementing the isosceles triangle with two even legs. Oh my god. Okay, what a harsh crowd we got here. Alright, dude, this stuff is funny. Oh my gosh. Alright, last one. Promise to laugh at this one. Who invented the round table? No? You guys? Circumference.
I'm done.
No, you get it? It's circumference.
Alright, we're back with the show. So, Mr. Pan.
Dr. Pan.
Mr. Dr. Pan, what were you saying about this parallax?
Huh? Oh yeah. Parallax is the apparent displacement of an object due to the different lines of sight.
What of what? From two different what?
Alright, let me give you an example. Put your index finger in front of you. Not too far, not too close. Now close one eye, then the other. Your index finger seems to have shifted left and right.
Yeah.
This apparent displacement is due to the difference in lines of sight.
And how do you apply this to finding distances between stars?
Let me show you. Well, in stellar parallax, the star's apparent displacement is caused by the Earth's orbit around the Sun. A triangle can be made from the two lines of sight from Earth to a star on either side of the Sun. And angle formed by the bisecting line from the Sun to the star is a parallax angle.
Simple enough. I mean, you just have to use sine again to get the distance from the star to the Earth.
It's even simpler. The units of measurements changes things up. The unit of measurement for the parallax angle is arcsecond, which is 1 over 3,600 of 1 degree. Stars are so far away that angle created is very small. The unit of measurements for distance is called parsecs. It is the distance to the star when the arcsecond is 1 and the Earth to Sun's distance is 1 AU. It gets easier from here. The distance to the star in parsecs is the reciprocal of the parallax, or the ratio of 1 to the parallax angle, in arcseconds, leaving you with the formula d equals 1 over p. where d is the distance of a star in parsecs and p is the parallax angle of the star in arcseconds. Now, let's stop here. Where did I just come up with that equation? Let's look at this drawing. Tangent of p, opposite over adjacent, is the radius of Earth's orbit at 1 AU, over the distance between the Sun and the star. The angle of p is very small, so that we can apply small angle approximation and say that tangent of p is approximately equal to p. In radians, we know that the a is equal to 1 AU, so plug that in. Now when you rearrange the formula, you get d equals 1 over p. Now back to the explanation. For example, the closest star to Earth with the exception of the Sun is Proxima Centauri. It has a parallax angle of 0.772 arcseconds. Now, we just plug it into the formula and get 1.30 parsecs, which translates to 4.24 light years. Other things you should know is that when doing stellar parallax, the distance between the Sun and the Earth and the star is considered equal because the difference in their distance is minuscule compared to its length, and the parallax angle is extremely small. However, this method only works for calculating the distance of closer stars due to modern technology. We can only calculate the parallax angle precisely at close distances.
Wait, it sounds so simple. It's actually pretty easy.
Since parsecond is the distance when parallax angle is 1 arcsecond, getting the ratio of 1 and the actual arcsecond will be the parsecond.
Well, thanks for coming in, Dr. Pan. I think that's all the time we have for today.
Tune in next week to see Carla and Gabriella perform I Ain't No Second Motor.
Goodbye.
Bye.
Bye.